Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Electrodes and Separator Materials for Redox Flow Batteries from the paper Energy Related Materials. So students, let us see what are we going to learn in this module. First, the basic components in a typical RFP. Second, what are the construction materials used in RFP? Third, what are the electrode materials, their type and their function in RFP? Fourth, what are the separator materials, their type and their function in RFP? So let us start with a basic introduction about this module. The hardware of a flow battery consists of flow field plates or bipolar plates which are sandwiching between the two electrodes separated by an ion exchange membrane, also called as membrane electrode assembly or MEA. Current standard practice is to use a zero gap architecture cell to minimize the contact resistance in the cell, thereby improving the system performance. A closure view of near electrode construction is shown in the figure. As you can see in this figure, so students note over here that there is a rubber gasket and steel tie bolts are normally used to compress the cell stack in order to avoid the electrolyte leakages. The end plates made out of metals such as aluminium and copper can be used as current conductors to provide electrical conductivity. Turbulence promoters can be employed in the compartment to increase the mass transport and exchange of electroactive species. Since electroactive species present in the electrolyte are generally highly oxidizing in nature, hence no metallic component can be placed in contact with the electrolytes. Chemically resistant polymers such as polytetrafluoroethylene or PTFE, ethylene polypropylene diene EPPD, polyvinyl chloride PVC, polyvinylidene or PVDF, and acrylics are the typical materials used to fabricate the RFP electrolyte compartments. So students, continuing our discussion over the construction materials of RFPs, the figure shows the schematic of the RFP cell stack. For practical applications of RFP, the unit cells are required to connect in series in bipolar configuration to form a battery stack. Hence, a large cell voltage can be obtained. In some circumstances, easily folded rubber tanks can effectively utilize the available space, such as in underground cisterns in the building. Now we will discuss about the electrode materials for RFPs. A perfect electrode material must have high electrical conductivity, good mechanical properties, and strong chemical resistance. Besides this, it must be of reasonable price and have a long life cycle in highly oxidizing atmosphere. Typical electrodes which are used in RFPs are based on carbon materials or inert metallic materials. Carbon-based electrodes, they are most common compared to the other metallic materials since carbon materials do not undergo the dissolution or the formation of oxide during chemical oxidation. So, the metallic ions from the metallic electrodes can dissolve into the electrolyte during the discharge, and due to their corrosive nature, which could result into the unstable redox potentials and disturbs the chemistry of RFPs. If metallic electrodes are utilized, they must be based on noble metals which possessed good electrochemical stability or the catalytic property. Some metallic electrode materials with high overpotentials for gas evolution have been used to facilitate the desired reactions and avoid the side reactions. Carbon electrode materials for RFPs. Carbon material based bipolar electrodes are widely used in RFPs. In past 2 decades, several carbon-based materials of different form, including 2 and 3-dimensional electrodes, have been studied. Typical 3-dimensional carbon-based electrodes include carbon cloth, carbon paper, and carbon felts. Since pure carbon and graphite are brittle and often difficult to scale up in stacks, hence carbon polymer composites and polymer impregnated graphite plates are generally used, which have advantages in their low cost, lightweight, and improved mechanical properties. Carbon polymer composites have been used in various systems such as zinc bromine, all vanadium, bromine polysulfide, zinc cerium, and soluble lead acid RFPs. These materials can be held together by polymer binders such as polyvinylidene fluoride or PVDF, high density polyethylene HDPE, polyvinyl acetate PVA, and polyolefin by injection molding. The injection molding technique is a low-cost technique that has the advantage of producing large amounts of carbon polymer composites easily. Further, a polymer impregnated graphite plate can be manufactured by compression molding the expanded graphite with thermoplastic polymers. Since this molding technique allows the use of a higher proportion of graphite than the injection molding method, it has better electrical conductivity. Due to the thermoplastic properties of the polymer used in this technique, the mechanical properties, chemical resistance, and thermal stability are superior to those produced by injection molding. Since longer time is required to cool down the mold before each half plate can be removed, the production cycle requires longer times. Therefore, the higher costs of this method could hinder its use in RFPs for large-scale applications. Conductivity of the above discussed composite materials can be enhanced by the mixing of conductive filler material or activated carbon particles in the polymer matrix. The high carbon content can lead to poor mechanical properties, and some investigations have reported that carbon black filler can cause undesirable reactions such as gas evolution and water decomposition, especially when the battery is overcharged. The oxidation of such carbon black filler could also increase the electrical resistance. Two-dimensional carbon electrodes were reported to be chemically stable for the redox reactions of V4 plus, V5 plus, and cerium 3 plus and cerium 4 plus due to the carbon dioxide evolution. Since these reactions occur at high positive potentials and local current density at the planar electrode surface underneath the carbon felt can be very high. Physical deterioration of the electrode surface can be observed by mechanically compressing the carbon felt onto the carbon-based collector used in the positive electrode. The all vanadium and the divided zinc cerium systems can operate at a projected current density of greater than 50 milliampere per centimeter square with a voltage efficiency of over 75%. Carbon electrode materials for RFPs. Three-dimensional carbon-based materials, they have been used in various systems due to the large surface area that is typically of the order of 240 to 400 centimeters square and 5 to 70 centimeters square for the carbon felt and the reticulated vitreous carbon foam respectively. The polyaryl nitrile, that is PAN, based carbon felt electrolyte is the most commonest electrode material used in all vanadium systems so far. The PAN based graphite felt has advantages in wide potential range due to its good electrochemical activity, high chemical stability, and low cost. So, however, several types of modifications have been made on graphite felt to enhance its electrochemical activity. For example, the graphite felt can be improved by treating it with sulfuric acid followed by the heat treatment. During the acid treatment, surface functional groups such as COOH and ClO were formed on the electrode surface, which was found to significantly increase the chemical activity in the highly acidic media. Some researchers have further improved the catalytic properties and the conductivity of carbon felts by depositing the metals on the electrode surface. For instance, Sun and Skylas Kazakos have modified the carbon felt electrodes through the impregnation with solutions containing ions such as Pt2 plus, Pd2 plus, tellurium ion, Mn2 plus, indium ion, and arsenic ions, and etc. So the students look into this table which list some of the carbon-based electrode materials used in various RFPs. The flow-through configuration has a more uniform concentration of electroactive species and gives an enhanced mass transport. It is often impractical due to the very low flow rate required and the high scale-up cost. Therefore, most flow batteries reported in the literature adopt the flow-by configuration. In this configuration, the electrodes are generally made up of two or three-dimensional materials corresponding to different electrolyte flow modes. Various three-dimensional electrodes have been used extensively in RFPs due to their large surface area, resulting in faster electrochemical reactions and lower polarization at the electrodes. So as you can see from the table that there are different electrode materials corresponding to the electrode material, we have different manufacturers which have various thicknesses, which is in mm, and they have the different electrode polarity. Corresponding to the electrode material, we have the different RFB systems. Metallic electrodes. Metal-based materials are less commonly used for electrode preparation due to certain shortcomings. These are corrosion, dissolution, and weight issues. While precious metals such as platinum and gold have excellent chemical stability and electrical conductivity, however, their high cost renders them impractical for routine large-scale energy storage. Moreover, precious metals do not necessarily show good electrochemical behavior. For instance, vanadium reactions are not reversible at a gold electrode, and platinum forms a non-conductive oxide film during the oxidation of cerium 3+. Passivation can also occur at other metals such as lead and titanium electrodes during V4+ oxidation. However, There are some redox couples including V2 plus, V3 plus and V4 plus, V5 plus are more reversible on metallic electrodes than on carbon. The redox flow reactions of Cr2 plus, Cr3 plus and titanium 3 plus, titanium oxide 2 plus are irreversible at carbon electrodes. However, it showed better reversibility at the metal surfaces such as amalgamated lead and tungsten rhenium alloy respectively. Next, we will be discussing about the metallic electrodes. V4 plus, V5 plus and cerium 3 plus, cerium 4 plus reactions were found to turn from irreversible at glassy carbon to reversible when carbon felts were used. Due to the high cost of platinum, a dimensionally stable anode or DSA has been used as the positive electrode in all vanadium and zinc cerium flow batteries. In general, a DSA electrode is manufactured by coating a titanium substrate with a thin metal or alloy oxide selected from the following group of metals such as manganese, platinum, palladium, OS, ruthenium, etc. In the study of Rijek and Skylas-Kazakos, an iridium oxide coated the DSA electrode was reported to have good reversibility for the vanadium reactions. In order to discharge a zinc cerium flow battery at high current densities, a three-dimensional DSA mesh stack electrode manufactured by spot welding three pieces of platinized titanium mesh has been used, which operates better than the two-dimensional electrode. Apart from these noble metals, some metals having a high overpotential for the gas evolution have been used as the substrate electrodes in several RFPs. For example, zinc nickel and zinc air RFPs, they have been used in hydrogen overpotential cadmium plated nickel sheet as the negative electrode to reduce the dendritic growth and to suppress the hydrogen evolution effectively. Three-dimensional nickel foam is another metallic electrode which have been used in sodium polysulfide bromine and suitable lead acid systems. The table lists the metal-based electrode materials which are exploited for different RFPs. So we have the different manufacturers for different metallic electrodes. Here there are 5 metallic electrodes have been listed, and corresponding to the metal electrodes we have a particular RFP. That is, for a nickel foam metallic electrode we have bromine polysulfide RFP. Cadmium plated copper corresponds to zinc nickel and zinc air RFP. Sintered nickel hydroxide corresponds to zinc nickel. Nickel foam lead corresponds to soluble lead acid, and 3D platinized titanium mesh metallic electrode are used for zinc cerium based RFPs. Separator or membrane materials. A perfect membrane or separator materials must prevent the mixing of electroactive species of the electrolytes flowing in anolyte and catholyte sites and the direct chemical reaction of active species can result in energy losses. Hence, permeation of the active species and the selectivity of the charge carrying ions throughout the separator are highly important. Typical separators for RFP are the IEM, which are fabricated from polymeric materials with a pore diameter of 20 angstrom. In aqueous electrolyte, IEM are designed to conduct positively charged ions or negatively charged ions by means of cationic or anionic exchange membranes, respectively. In a recent paper on lithium ferricyanide flow battery, a solid electrolyte separator is utilized to transport Li plus ions and effectively prevents the aqueous positive electrolyte from reaching the negative electrode. The ideal membrane for an RFP should be chemically resistant to aggressive species and exhibit low area resistivity to minimize the ohmic losses. Ion exchange capacity is often used to measure the charge carrying ions passing through the membrane, and the conductivity of the membrane is determined by various factors such as thickness, ionic group concentration, the degree of cross-linking, the size, and the valence of the counter ions. According to Vefiades and Skyles-Kazakos for IEC, there is no direct correlation observed between resistivity, diffusivity, and the membrane thickness for the vanadium electrolytes. Electrolyte concentration and ion exchange groups with the separator are highly affected by water uptake and hence the degree of swelling. With a high degree of cross-linking, better selectivity was observed with less pronounced swelling or water transfer across the membrane. Although the transfer of vanadium ions through the membrane was found to be highly dependent on the concentration difference between the positive and the negative electrolytes. Cation and anion exchange membranes tend to have net volumetric transfer towards the positive and the negative compartments, respectively. Separator or membrane materials. A perfect membrane or a separator material must prevent the mixing of electroactive species of the electrolyte flowing in the anolyte and catholyte sites and the direct chemical reaction of active species can result in energy loss. Hence, the permeation of the active species and the selectivity of the charge carrying ions throughout the separator are highly important. Typical separators for RFP are the IEM, which are fabricated from polymeric materials with a pore diameter of around 20 angstrom. So, in aqueous electrolyte, IEM are designed to conduct the positively charged ions, that is H plus or Na plus, or negatively charged ions, that is Cl minus, NO3 minus, or SO4 2 minus, by means of cationic or anionic exchange membranes respectively. In a recent paper on lithium ferricyanide flow batteries, a solid electrolyte separator is utilized to transport the lithium ions and effectively prevents the aqueous positive electrolyte from reaching the negative electrode. The ideal membrane for the RFP, it should be chemically resistant to aggressive species and exhibits the low area resistivity to minimize the ohmic losses. Ion exchange capacity, or IEC, is often used to measure the charge carrying ions passing through the membrane, and the conductivity of the membrane is determined by various factors such as thickness, ionic group concentration, the degree of cross-linking, the size and the valence of counter ions. According to Vefiades and Skylas Kazakos, for IEC, there is no direct correlation observed between the resistivity, diffusivity, and the membrane thickness for the vanadium electrolytes. Electrolyte concentration and the ion exchange groups within the separator, they are highly affected by water uptake and hence the degree of swelling. With a high degree of cross-linking between the selectivity was observed with less pronounced swelling or water transfer across the membrane. Although the transfer of vanadium ions through the membrane was found to be highly dependent on the concentration difference between the positive and the negative electrolytes. Cation and anion exchange membranes tend to have net volumetric transfer towards the positive and the negative compartments respectively. Compared to an anion exchange membrane, the cationic counterpart tend to have lower area resistance per thickness due to higher solubility or mobility of the H plus ions compared to the anions. This explains the fact that a cation exchange membrane is the most widely investigated membrane material for VRFP. However, the chemical stability of different IEM could vary from each other depending on their chemical structure. In general, IEM based on a perfluorinated backbone, particularly the nephine cation exchange membrane, have superior chemical stability to the most types of hydrocarbon membranes. However, recent studies suggested that AEM could effectively reduce the crossover of vanadium ions in VRFP due to Doman exclusion effect, which is an electrostatic repulsion between the cation groups within the membrane and the electroactive species. So, the development of IAM for vanadium RFB has been reviewed and concluded that Nephyon, although it is expensive, is still the most used membrane, but other alternatives such as modified Nephyon and pore-filled composite membranes with new polymers and new materials should receive more attention in the future. So, students, let us summarize what we have learned in this module. The hardware of a flow battery consists of flow field plates or bipolar plates sandwiching between the two electrodes separated by an ion exchange membrane, also called as the membrane electrode. A perfect electrode material must have high electrical conductivity, good mechanical properties, and strong chemical resistance. Besides this, it must be of reasonable price and have a long life cycle in highly oxidizing atmosphere. Typical electrode materials used in RFBs are based on carbon materials or inert metallic materials. Carbon-based electrodes are more common compared to the metallic materials since carbon materials do not undergo dissolution or the formation of oxide during chemical oxidation. Metal ions from the metallic electrodes, they can dissolve into the electrolyte during discharge and due to their corrosive nature. This could result into an unstable redox potentials and disturbs the chemistry of the RFBs. Thank you.